All right, so we're beginning a new chapter on balancing. First will be about rotating masses, and then towards the end there's a section on static balancing, in particular 4-bar linkages. Again, static balancing. For rotating masses, some general concepts. I begin here with an example. This is a small casting centrifuge. It operates in an enclosure like a bucket, and it's used to cast jewelry. This is a crucible. Use a torch. Of course, it's not rotating. Use a torch to melt the precious metal, and then you turn the motor on, and this accelerates to steady state. Centrifugal force forces the molten gold into the mold, and you get the ring or jewelry. I'm pointing you to the counterweights here. So there are 4 discs, could be others added or removed, and their the mass, total mass, as well as their location relative to the axis of rotation could be adjusted. For what reason? We don't want this to shake as it's spinning, and you calculate how much gold you're going to melt, and based on that you decide how many masses and at what location. I could use only 3 discs positioned further away, or add 1 disc and move the package of 5 closer to the axis of rotation and achieve the same condition, that is, the overall center of mass of the unit to be on the axis of rotation. This way I get, well, in practice will be some small residual unbalance, but I get a smooth rotating of the centrifuge. Also notice that the axis of the counterweights is through the crucible, and the mold will right here. So and this is on purpose. I don't have the discs high up or below. Okay, so we identify one condition for achieving balancing of rotating masses, that is the center of mass to be on the axis of rotation. And this is pretty obvious. This is not enough to achieve smooth rotation of masses in practice. And really many rotors in everyday life in practice, there are bodies of revolution. Shafts are cylinders, possibly in step, but there is an axial symmetry, and we'll have the center of mass on the axis of rotation, as well as the axis of rotation being geometric axis for the body. If you have a fan, for example, with multiple blades, the blades will be equally spaced. On tires, everybody knows balancing tires. You do balancing of tires because they cannot be fabricated precisely even. There will be some variation in the rubber distribution. The metal wheel itself will be balanced inherently because it's made symmetric, like a body of revolution and homogeneous material, but the tire won't be. When we discussed motors, I passed around for you to study wound rotors, and I pointed to places where mass is being added, that is solder, and then where mass has been removed. And that happened on 2 faraway planes close to the ends of the shafts, if you remember. Anyway, so we're looking here at a disc, homogeneous disc, that is rotating about a vertical axis through the geometric center of the disc. And imagine this being chucked into and you spin it with a corded drill, and you spin it fast, and you don't sense it shaking. However, if the axis of rotation is not through the geometric center, but rather offset by the amount E, then, and you spin it, angular velocity omega, there will be a centrifugal force mass times angular acceleration, which is E times omega squared. And this centrifugal force will rotate. And if you hold that handrail with your hand, it will shake your hands. Why? Because we have this force that is going around and around and is transmitted to the bearing, and it causes a reaction force that is constant in magnitude but is rotating. Also causing a moment. So because I have the bearing below the plane of the disk, the amount of this amount, let me change to thicker. So this amount, and I said it's red. Okay, so this amount L is going to, because of this amount L, this offset of the bearing, there will be a moment M that is L times Fi. So we are going to see both a rotating force as well as a rotating moment. And so, and these are called shaking force and shake moment. So, and a situation like this, it's called static unbalance. Why static unbalance? Because we can tell the state of unbalance without rotating the disk really. Imagine this bearing having negligible friction, and you rotate it in a horizontal to where the axis of rotation is horizontal, and this will settle like a pendulum to the lowermost position, where the center of mass, it will be in the lowermost position and on the vertical with the axis of rotation. Okay, and then we have this case. This case is of a wobbling disk, and this too causes shaking to the foundation of the machine, if it's a machine, or shakes the hands of the person that holds that drill while it's spinning. I have the center of mass on the axis of rotation, but here the disk is not in a plane that is perpendicular to the axis of rotation. Imagine this line perpendicular to the line of maximum slope. So I delimit two half disks, and each of the disks will have its own center of mass. Mass divided by 2 corresponds to 1 half disk, and the centrifugal force now is going to be, we can determine there are ways of getting it, or it's tabulated if you take any search online or static dynamics books. They do have geometric properties, strength books. So we can find the amount of the distance from the center of the disk to the center of mass of 1/2. Of course, we need to know the angle of the angle at which the disk is positioned, and we can calculate the distance measured from the center mass of half disk to the axis of rotation. We call this E. So there are two forces equal in sign, but at a vertical offset L, that's going to cause a moment, a rotating moment, a shaking moment. And this moment, or rather the force of this couple, this is a couple, is going to be eccentricity E times mass of the disk by 2 times omega squared. Okay, so this is a case of dynamic unbalance. We cannot tell the state of unbalance using gravity. So I'm sorry. So if you're holding the axis of rotation, bearings, negligible friction, horizontal, this will not have a preferred position to where it rests versus this one. So if I turn this and make it horizontal, then the axis of rotation, with the axis of rotation horizontal, this will have a preferred position, okay, corresponding to the lowermost point of the center mass, which is the center of the disk, relative to the to the axis of the hinge. Okay, so let's go back to the notes. Recognize the condition of static balancing, that is the axis of rotation to pass through the center of mass. Condition of dynamic balancing is for the axis of rotation to also be principal axis of inertia. Principal axis of inertia are always through the center of mass. So you cannot have dynamic balancing without achieving static balancing. And getting the axis of rotation as principal axis of inertia, it's easy to achieve for homogeneous bodies with symmetry. So if you have a cylinder, if you rotate a cylinder about the longitudinal axis, or if you rotate it on about any perpendicular axis through the middle of the cylinder, then it will be balanced. Spheres, any axis through the center of the sphere, solid bars, the same. If there are multiple solid cylinders, then if they are coaxial, the axis, their longitude axis, the principal axis of inertia. Okay, so let's assume in this case I have a lump mass and it's in gravitational field. This is the weight, and if I rotate by omega, I'll be also having a centrifugal force. I can sense by slowly rotating, where omega is negligible and centrifugal force is negligible, I can sense the unbalance as a moment that is changing in magnitude. Moment is going to be 0 when the arm is vertical, either above or below, and it will be maximum when the arm is horizontal. As I'm rotating this increasingly fast, then the centrifugal force takes over, this becomes negligible, and it's going to create that reaction force. It's rotating, as well as a moment caused by this inertia force and the length L of the arm. So there will be a rotating force and a rotating moment. Shaking force, shaking moment, the imbalance you have here, there are X and Y components. Rather, for the moment about the Z-axis, and force over components of the reaction force over X and Y. If I rotate the same mass about the vertical axis, I can tell the condition of static unbalancing, recording a fluctuating moment over X and Y. And then while reaction force is constant, equal to m times g. As I increase the speed, then there will be a radially pointing, is not shown here, force, inertia force is causing the shaking of the bearing. There will be both a rotating force and a rotating moment, similarly to here. Now, if we take the case of multiple masses, lump masses, disposed about along a rotating shaft, and we have the mass m1, m2, m3, generically mi, I not for inertia, but rather as an index. And then we have lengths from A to A1 will be L1, A to A2 will be L2, A to A3 will be L3. And again, I can have more than 3 masses. And then there are at the ends of the shaft, A and B. It's there where we'll consider towards the end placing counterweights to fully cancel the shaking force and shaking moment due to unbalance. But let's look first of static balancing, that is having these radial forces, the centrifugal forces, being added to 0. So static balancing can be achieved by using just one counterweight. If I want to bring the mass, center mass of the assembly on the axis of rotation, all I need is just one mass placed anywhere along the shaft, and and the mass has to be correlated with the distance, and of course the angle of the orientation angle has to be properly determined. So if you look along the shaft, you have the three masses, the inertia forces, and here it shows the counterweight. MBal distance from O to the center of mass is R, and the effect of the inertia force of the counterweight together with the inertia, the three inertia force of the existing lump masses, it's going to be 0 for static balancing. This is the vector polygon showing how they add up to 0. So the scalar equations made by these three inertia forces and the fourth force caused by the counterweight need to be equal to 0. So the omega squared is no longer occurring here, because, or rather is considered 1, because the state of balancing or unbalancing is not dependent of RPM. Of course, the higher the RPM, the larger the magnitudes of the shaking force, shaking moment, but otherwise the state of unbalance or balance is not depending on RPM. Okay, so in general, I could, if you know, I call this angle theta I, MI, RI, I project with cosine over x, with sine over y, you know, these. So these are the sums. And then I'm having the additional mass separate MBal, RBal, cosine theta bal. And for the y-axis with sine. I can find the angle right away. I can just move the sums to the other side, take the ratio. MBal, RBal simplifies out. I get second divided by first after I separate the sum on the other side. So I get tangent of theta bal equals sum of MIRI sine over sum of MIRI cosine. So I have the angle. I can go back to any of the original equations and I can solve for the product MBal, RBal. I cannot, again, there are two equations and I have 1, 2, 3 unknowns. It is the angle, radius, and counterweight value. So balance could be done with a smaller mass at a bigger distance or a bigger mass at a smaller distance. Something that's done in practice, maybe you know, on balancing crankshafts, there's a dense material used. That is tungsten alloy for compactness. Okay. Now, to achieve dynamic balancing, I want to have forces summing to 0 and moments summing to 0 as vectors. More explicitly, there will be a two counterweights used. So let me take the screenshot and I go to here and say paste, and so there will be a counterweight mounted here at some angle. It will be theta A, and then there will be another counterweight here. I'm sorry, or rather we'll have it here, and I measure the angle. And this will be the angle theta B. I have MB, I have MA, and of course this will be RA and this will be RB. I want to know location A and B are given. A, it's at the origin of the reference frame. B is at some distance. I need to know the distance AB. Same as I need to know the distances OA1, that's L1, OA2, that's L2, OA3, that's L3. Okay, but a system, it's considered balanced, fully balanced, if the sum of the inertia forces, centrifugal forces of the original masses and of the counterweights sum up to zero, as well as the moments caused by all these forces. MA does not cause a moment because distance is zero, but 1, 2, 3, and the fourth mass moments caused by these over x and y should equal 0 to achieve balancing. So this is what these two scalar equations mean. We have the same sums as before, as for static balancing. Okay, now they occur on the other side. The counterweights being 2, of course, I need to have 2 angles, 2 masses, 2 distances from the center of the mass to the axis of rotation. Okay, so how do we go about solving these 4 equations with how many unknowns? There will be 2 angles and 2 R A, MA, RB products will be 4 unknowns. We can solve for the angle from the second equation, taking the ratio. So if you look here, if I take the ratios of the 2, we obtain the angle theta b, and then so this is one. Again, the mass A does not cause a moment. It's if I go back to this, so mass A does not cause a moment. So I can solve for theta b from the third and fourth equation, and then I can come back with a known angle, and I can solve from any of the 2 equations for the product MBRB. So I have the angle and I have the MBRB product known, and I go now to the first 2 equations and I can solve for MARA and theta A. So this is the process. Everything can be placed in a spreadsheet that is expandable. I can, again, the sums here could be of more than just 3 terms, and implementing this equation first and then solving for the remainder unknown makes the problem or solves the problem completely. A working model, of course, working model is a 2D simulation software. I cannot do dynamic balancing analysis, but I can do static balancing analysis. These are 3 lump masses as they originally were, and you can see the sine waves for the X and Y shaking force. Okay. Let's look at the process of balancing rotating masses. The need for balancing is clear. You have wheels with tires. They need to be balanced. If they are unbalanced, particularly on the front wheel, you can sense the steering wheel, the shaking. Rotors of particularly the wound ones, or the wound ones of rotors of electric machines need to be balanced. The way this cradle balancing machine works is can be explained better with reference to one of the lab experiments that I believe you're doing in engineering lab. So at resonance, if you have a spring mass system at resonance, there is a 90-degree phase difference between the unbalanced force or the excitation force and the response. And the way this machine is operated is to allow, it's driven by flexible coupling, and I allow it to oscillate either about a wedge here or on the other end. And so I'm running at resonance, and let's say here's not explained how the phase angle is measured, but for that lab experiment, let me start new. I don't save it. So with direct reference to that lab experiment, so we have a disc with a missing large disc that's rotating and has missing material to it, which causes excessive material to be present on the other end. And this is mounted, and it's rotating. It's mounted on a beam which is pinned at one end, okay, and then there is a spring on the other end, okay. The disc has divisions to it from 0 to 360. There is a reference mark, and then you have a moving contact you can adjust, and when the arm is in the uppermost position that you have maximum displacement, there is a contact that's closing. You have the stroboscope flashing light, and you can read what value on the disc is in alignment with the reference on the stationary reference. So say I don't know where the excess mass is. I don't, and I want to do balancing. So what you're doing, you're running the motor. Adjust the speed until you have maximum oscillation. That's resonance. You're flashing the light, you adjust the contact so that flash is done when the beam is in the maximum vertical displacement. And you remember what number was in alignment with the fixed mark observing the strobe light. And then you stop the machine and you make your bring the disc. Say I read 43 degrees. Line 43 degrees was the stationary mark. And we know when we have maximum displacement, and if the disc is rotating in this direction, so at maximum displacement, at resonance occurs when the shaking of the forcing force was had passed, and it's 90 degrees ahead. Okay, so essentially you bring this in alignment, and so I have the disc separate. I said 43 in alignment with the mark. I know that the heavy part was ahead 90 degrees, so all I need to do is just remove mass opposing to it, and not that this is calculated, it's done repeatedly. It's what this says. So you remove mass on this when you allow it to oscillate about this fulcrum. You remove mass on this plane, and then you lock this pivot, and you release this other one. You oscillate the other end, and you do the same, run it resonance, figure out where the heavy spot is, remove material from the heavy spot, or add material on opposing. And you do this until the amplitude of the oscillation is a minimum. Okay. So again, visit the lab experiment that's done. I can go and say tech equipment. And maybe rings a bell. So it's this one. And for this one, I move it to where it's in. All right, and oh, doesn't look right. Wow. Anyway, so this is the beam, this is the fulcrum, this is the disc that's rotating. You adjust the speed from here, you read the RPM from here. There is a moving contact. Now, this is the spring, this is a paper strip that's moving. With a pencil you record the oscillation. Okay, all right. Let's see. The last part of this chapter is about static balancing of linkages. And static balancing, it's for slow-moving systems. Everybody knows of the use of springs for static balancing of like this lamp, or using counterweights that change configuration for this other type of lamp. And I do have some examples that I can, for example, you're familiar with this, so the use of springs for balancing, the use of counterweights for, so the use of a counterweight which is moving, it's hinged with the arm of the crane to achieve balancing of the dead weight of the arm. And then there are other examples. There are manipulators that use counterweights, so to minimize the effort of the operator as it's moving the payload. Okay, so for that, those instances we have like use of springs. We have potential energy of the springs and potential gravitational potential of the masses that move in the vertical plane. You want to have the total potential energy not to change as you reconfigure the system, and likewise with this one. So there's a linkage that's connected to this mass, and it doesn't have a preferred position, so that the potential and gravitational potential energy of the whole system with the masses reconfiguring is not dependent on the angle of the arm as well as the orientation of the shade. We'll be more specific. We're going to look at 4-bar linkage static balancing, and this would be applicable, say there will be an assignment I'm going to issue, so it's applicable to, say, level looping crane balancing. So I'm going to kill this and let's search for level looping cranes. Level looping crane, and all right, so or elsewhere. Okay, so this crane is a 4-bar. It's a 4-bar, and although it uses a counterweight that is hinged here, but we can consider the balancing of the 4-bar of the looping crane the way it's explained in the notes. Here again, a level looping crane. Remember, this point is moving almost rectilinearly, and the choice of balance is to use a counterweight on this arm that is hinged, but yeah, the balancing could be done other ways, and for a 4-bar, and we are going to inspect this. Okay, so one is to use to do what is called 2 mass of static balancing. So you start with a 4-bar, and we're assuming the coupler to be made of 2 lump masses. We lump one here when we lump one here. If the center mass is right in the middle, that's easy. I'm just going to take half of the total weight. I'm assuming to be a lump mass at A, the other half lump at B. Okay, so now we're dealing with 2 masses that pivot about points 02 and 04. And we know how to balance those. You learn this in statics. So we'll add a counterweight, which was going to induce full balance, static balancing of this link 2 together with the lump mass portion coming from the coupler. And then likewise here have the lump mass together with the original link and the counterweight calculated, again distance in mass. Product could be a smaller mass further away or a bigger mass closer to 04, and likewise on this other end. And we get balancing. The second approach using 3 mass balancing is to take the link that is coupler and add a counterweight that will bring the center of mass of the assembly made by the link 3, the coupler, with the counterweight at the distance R4. Bring the center mass at A. So now we have the link 4 by itself, and we have link 2 with the mass equals to the mass of the coupler plus the mass of the counterweight that we need to balance. And we do the same. We're going to place a counterweight that will bring the center mass of the assembly at O2, and link 4 by itself together with the counterweight, the center mass of the assembly now it's 404, and we have balancing. Okay, so this was it. I do have some working models. So alright, so this is the original 4-bar, and as you can see, this is a vertical plane. I have gravitational pull or gravitational force present, and it has a preferred position. Working model allows you to display the center of mass of an assembly of bodies, and as you can see, preferred orientation is where, and I added some damping to where it settles, where you can see. Alright, so it settles to the same position, which corresponds to the minimum potential energy. Right, so this is the 4-bar and it's in original position. Come on. Okay, looks like I need to kill it. Some conflict with the close the program. And then now with the counterweights, 2 counterweights calculated as explained in the text, if I hit run, it doesn't have a preferred position. So it stays where it is. Stop, reset. Well, it looks like there is a conflict between the recording software and working model. They don't like each other. Close the program. I'm going to show you the other example. Actually, it's the same. I have it. Open it. I clicked on the same. Application. No, this is something else. This is to show that static balancing doesn't mean that if I have it driven fast enough, I'm going to experience no shaking of the foundation. That's not the case. So let's stop, kill, close program. Let's look at the one with 3 masses. So okay, so now this 3 mass balancing, it doesn't have a preferred, it's gravitational field, but does not have a preferred. This is the center of mass, and the center of mass is going to just move along at most. Actually, it remains in the fixed position. So the overall center of mass of the assembly is not changing location, and it means that the system does not have a preferred equilibrium position in the gravitational field. Okay, so this being said, I hope you enjoy the recording, and Wish you well.